Hello. I'm here now. Is the right place? I hope it does. Yeah. Okay, I assume all of you can see me. Okay, so a bit sorry for being late. And other people, could people hear me, by the way? Maybe maybe they can, oh. People can see me. Actually not too sure. Okay, let me try something. Okay, yeah, sorry. I am not the most familiar with this. So yeah, yeah, as long as y'all can see me, that's good. Feel free to use the questions. Like I'm pretty sure that's the only way for you all to interact with me. I don't think if you guys can use the chat, that would also help. But yeah, so I just want someone to know that I am just not speaking to the air. Okay, thank you. Let me share my screen. Again, I'm sorry about this. I can send out a handout afterwards. So here are some warm-ups. I think since I am kind of late, I will not go over these for too long, but there are two of them. There is this little advertisement diagram that I believe was used. And so the first part is to find the little shaded area. This is just like 7, so it's just 49, right? And like, tell me if I'm going too fast. Like, like the area of this whole thing is 49, right? And so when we're looking for the total area, then what we'll do is we'll use something called like the principle of inclusion or exclusion. Can I zoom in? Is this actually zooming in? I can't tell. Yeah, okay. Yeah, with respect to the files, it's so hard to see the screen. Do you guys not see? You guys not see like what I'm writing here? Or is there like a problem somehow? I'm actually not too sure. Yeah, so when you say it's hard to see the screen, what do you mean? You can keep typing. Okay, as long as I just want to make sure that you guys can all see what I'm doing. I don't want to make it like I'm like scribbling and it's really blurry, because I know that there's some classes that I've been like, oh, they're all blurry and I can't see anything. It's really frustrating. So I hope that's not the case. Anyways, so then for part B, when we're looking for the total area of points in either square, then we want like this whole area, right? And I mean, you can do this in multiple ways, but the way like that was sort of intended in this warm-up, and I sort of planned to make this a longer thing, but unfortunately that did not happen. Then we're just going to do 100 minus 49, which is the area of this L-shaped thingy, and then the area of this whole thingy then is just 100. And so our answer is 151, right? And that's the area of the points in either square. Alternatively, you can do this another way. You can instead extend this and subtract away the 2 squares. So that would be, 169, which is, 13 squared. And then we'd subtract away 9 twice, and then we'd get 151 as well. And then this is another warm-up. This is just like practicing with that Pythagorean theorem, because when we deal with areas, we will still need to deal with lengths, because like inevitably you cannot, you will rarely be able to do things where you can only do areas alone. So we're gonna have to work with this. Then we do to parse the conditions, right? When we say perimeter 52, that means that since it's a rhombus, all the sides are the same length. So this is 13. And then, this thing is like 12 when we intersect it twice, because it, bisects it. And so then this thing is 5, and, the whole thing is has an area of 120, right? This times this over 2 times 4. And I won't go any further. So these are the notes, I guess. If you want to like, if you really need to take notes, if you're that kind of person, then I included some facts that I think are important. And yes, like this notation, let like this denote the area of a polygon, right? Like for example, like ABC, the area of triangle ABC, right? And so the first theorem is what I was alluding to earlier, the PIE, or principle of inclusion and exclusion for areas, right? When we have like areas, then the area of the total thing is just the area of one thing plus the area of another thing plus the area of the intersected thing, right? And that's sort of the claim, right? And we use this a lot like we do PIE in combinatorics problems. And we intend to implicitly use this when we separate areas into multiple parts anyways, as like earlier, for example, right? When we did the 2 squares, then what we did was we took, you know, a little thing, right? And then we took a big thing and we added them together, right? But what we could have done is we could have rephrased this as just this plus this minus this, right? The small one. And that would have been fine as well. And let me know if you have any questions. Yeah. So this is like the first important like areas thingy that you will need to use in practice. Then there's the ratio of bases to ratio of areas, quote unquote theorem. Then, for example, if we have some points on a line, right, like say call them, you know, A, B, and C, and we have a point D here, then the ratio of the area of ABD to ACD is simply the area of AB over AC. And this is because, as I outlined here, there's a proof, right? When we have this length, the height, then the area of ABD is, you know, H times AB over 2, right? And we all know why this is true, right? You know, since you're taking this class, you still know something about this kind of thing. And then the area of, you know, ACD is similar, right? H times AC over 2. And when we take the ratio, then it's just AB over AC. And then finally, corollary 3.3. Well, again, termed as such, but it doesn't. I hope this should be at least, you have seen most of this before, I hope. Then the area of this little triangle compared to the area of the bigger triangle, then the area of ADE over the area of ABC is AD times AE over AB times AC, right? And so that's how you get the ratio of areas. And this is true even if you extend like E beyond C or something. And this is true because you can apply it twice, right? You can like do it here, right? And then the ratio of, you know, ADE over, you know, ABC. Also, let me know if you can't read something. I know my handwriting is not great. Then this is like AE over AC, right? And then the area of ADC, should have given myself a little bit more space with this handout. Then the area of ADC over the area of, you know, ABC is AD over AB, and multiplying, then we get, you know, ADE over ABC equals AD times AE over AB times AC. All right, now we're going to move on to some examples because I think that most of these things you have probably seen before, and so are likely to not be too interesting. Again, let me know if I'm wrong. And so we're going to go through some examples in roughly increasing difficulty order. I will try to get through. I do not think I will be getting through all of them, but especially the last few, they're actually hard. But I will try. Then this is, you know, number 12 from an AMC last year. So this again is not expected to be too difficult, but I still think that it's an instructive problem. Then, you know, these are perpendicular, right? And MV equals CU, right? And we want to find the area of the whole thing, the big thing, right? So first, we don't actually need to know anything about this point. This point is like known as like a centroid G, right? But the first thing is, if you already start working with that point, you start trying to figure things out, then you end up with problems. You end up spending too much time on the problem. And this being a number 12, you want to be able to solve this very quickly. Like you want to be able to get this done in less than a minute, right? Because you know, you want to get a good score. Maybe if you want to qualify for something, then you want to be fast. Then you don't want to find any like small points, small length, small ratio. That takes time. So the way I'm going to explain this is okay, that's not what I'm trying to say. Instead, we're going to try to find an area, right? And then we're going to try to see what we can do with that area, knowing what we know about the lengths, right? We know that this is true, for example, right? Then I guess I can ask you guys a question. What is the area of UVMC? Or UVCM, I guess. And I encourage participation, but I'll wait a little bit. And then what's the area of this little trapezoid? Okay, maybe this is confusing. So, yeah. Okay, thank you. Thank you. Someone responded. 72. That's right. Because the length of this is 12, and the length of this thing is 12 too. So we do 12 times 12 divided by 2 is 72, right? And then what ratio is UVMC over the whole area? Again, this should not be too bad. You just sort of explain how this works. Yep, 3 over 4. Thank you. So we know that like AUV over ABC is, I'm purely looking about this. So then, UV, CM over ABC is 3 over 4. So we can easily find the area of the whole triangle instead of having to use the fact that, MG to GV is 2 to 1. You may have learned this in, your geometry classes, or, you might see something sometimes. But without using that at all, without trying to do too much math, then we can solve this problem rather quickly. Of course, I took some time to explain it, but generally that's what I'm trying to do. All right, then this problem. So each side of a unit square is also the one side of an equilateral triangle that lies inside the square. Then we want to find the area that is, the intersection of all these things. Then I don't think I've drawn a very good diagram. It's not like that. So something inside here. I feel like I'm drawing a really bad diagram. This is really not helping. Let's try again. Some tools for this. Okay, this is not working, but okay, how am I going to make this make sense? So where are these points with these things? These things are, so far from the sides. This is like 15 degrees, right? Sorry, I'm kind of tired. And so these intersection points are, 30 degrees from the sides, and these are 15 degrees from the sides. And the angle between these two is 120 degrees. Yeah, this is true. Okay, and the area of angle between these two is 120. So, and then, I think I'm gonna skip this one. I didn't. I think I anticipated having a diagram for this, and I just didn't. And so the idea, anyways, is that you draw a better diagram than I did here. You actually get a ruler and compass and actually draw a really good diagram, and you find out how this works. Unfortunately, I do not have a ruler and compass, and so I cannot explain this to you very well. But you're supposed to use the areas for PIE for areas thing. I just don't perform this one. Luckily, here's an easier example. Okay, you can tell I just got back from somewhere because So in triangle P, this is an AIME problem from 2019. Maybe you all are too young for this now, but I took this test, I believe. No, I didn't. I didn't take this test. I'm lying. But I remember when this test came out because I did really badly on it when I marked it. Anyways, in triangle PQR, PR equals 15, QR equals 20, PQ equals 25. Points A and B lie on PQ. C and D on QR, and E and F on PR, such that PA equals QB equals QC equals RD, sorry, no, C, yeah, RD equals RE equals PF equals 5. And, this is a 15, 15, 20, 25, right? And this is 5, and this is 5, and then we have these little things. This is 5, and this is 5, and this is 5, and this is 5. So I will tell you this, if you try to calculate the area of the hexagon immediately, then you will have a problem. It will not be easy. Because, you're not going to be able to find a way to make the hexagon something you like. It is not something you like, and you'll have to use half-angle formula or some trigonometric stuff that is not easy. And I did not, and this is not why I put this problem here. It is, intentionally, this is not supposed to be something that you do like this. But we can, but like much like how we like sort of prove like shoelace formula, for example, right? Then what we try to do is we, take a thing and then we cut things out of it, right? We like draw things, some lines, and then, we cut the triangles out, right? Instead of trying to find out, how we can cut this thing up into pieces, then this is hard, right? There are 5 pieces here and there are 4 pieces here. And to calculate these things is a lot harder than to calculate, these things. And so, first of all, I guess a quick starter question. What is the area of PQR? This again should be very easy. And maybe I lost a few of you, but yeah, okay. Yeah, 150. So then that's the area of the whole thing. And so we want to find the area of these little small triangles, right? And how are we going to do this? Then we're going to use the same ratios thing. So what is the area of one of these small things? Well, let's do this one first. Then the area of this small thing is 5 over, 15 times 5 over 20 times the area of the big one, right? Then the area of the big one is, this 150, as we said, right? And so the area of this small one is then, that sort of much, quote unquote, percent of the area of the original. And this is 1/12 of the whole thing. And we're not going to find out what this is. We don't care, right? One of the important things is that you always want to keep things in terms of more complicated things. There was a problem in the AIME this year, and this is kind of an extra thing, but I wanted to talk about this because I think that contest philosophy is important. Then there was a problem in the AIME this year that had huge numbers, some really dumb numbers. It was 150, and the numbers were big, but you also had to square them. And turns out you do not care what exactly the values are, so you can scale them down to however small you want, right? If you have 150, 200, and 300 or something, then you can scale it down to 3, 4, and 6. And of course, make sure to remember, mark somewhere on your paper, do something about it. Make sure to remember to multiply by 50 afterwards. But at least for the purposes of, the structure of the problem, then it does not matter if it's 3, 4, and 6, or 150, 200, and 300. That doesn't really matter. Right? So we're going to do this for now. And then similarly, the area of, APF or whatever is just, 1/3 times 1/5 times 150. And similarly, 1/4 times 1/5 over 150, times 150. Right? And so this is, 1/12 plus 1. Then the sum of the areas of the triangles is this, right? And so this is just I will save you the calculation and tell you that it's this, or 1/5 of the area, right? Which means that the area of the hexagon is 120, right? Which is 4/5 of this, right? And that's how you do this problem. And again, this is sort of an easier problem that you'll see earlier in the test. But I think that sometimes these kinds of problems actually tend to intimidate people. People tend to spend too much time on them. And one of the important things about math contests is that you need to be doing things fast. I think that, of course, you want to be able to learn math, you want to be able to understand it. But in contests, you don't just have the luxury, you don't have the luxury of researching the configuration for, an hour. You do not have this time. And it is easy to take too long. Then what you're going to be trying to do is you're going to be trying to do the problem in the least time possible, because otherwise you're going to be burning a lot of time. Okay, here's another problem from CMIMC. So rectangle, this order, then x lies on CD, and then bx and AC intersect at P. And this is area 3, and this is area 2. And we want to find the area of the entire rectangle. So first of all, like boilerplate, I guess. What is px over bx? Or sorry, not p. Sorry, this is confusing. More even easier. What is xp over bp? Given that we know the ratio of the areas. Yes, exactly. 2 over 3. And this is because of what we said earlier, right? The ratio of the areas is the ratio of the bases, right? And this is true even if, in any order. So as long as they are on the same line and the point is the same, then the ratio is 2 over 3, yes. So this is 2 to 3. So then this is like, well, I will use variables because, you could probably do this without. And then we can find, the area of this thing, right? What is the area of this thing? Like, okay. First of all, what now is AP over CP? If you people have seen like similar triangles. Oh no, lost. Okay, so do you see how we know the ratio of XP over BP? Okay, so then have you seen these triangles being similar before? Have you seen this configuration before? Yeah, okay. Yeah, so yes, 3 over 2, exactly, thank you. Then that's the ratio of AP over CP, which is then the ratio of ABP to ACP, or sorry, PCP, PCB. Okay, so then the area of ABP is 9 over 2, right? Now we can find the area of ABC. We see why this is very quickly giving us the answer, right? The area of ABC is just this, which is, 15 over 2. So the area of the whole rectangle is just 15. You can probably do this quicker, by the way, actually. I actually did, quote unquote, waste a little bit of time. The area of this turns out to be BCX, turns out to be 1/3, because this is 2/3, this space is 2/3, right? So then you can find like this, like the whole area of this thing faster. But in any case, we have found the area to be 15, right? And that's how you do this. And so make sure to remember these similar triangles. I mean, this is technically not exactly what I planned to cover at all, but it is an important thing to remember to look for these similar triangles on parallel lines, because when you have, something like this, then you will always get these similar triangles, right? So they will always be there. Make sure to look for them, and make sure that, like, when you have these sort of rectangle problems, you are able to very quickly do them. A lot of people make the really, really sort of inefficient decision to decide the coordinate bash these. This is a bad idea. Getting too used to coordinate bashing, I know people love it. I know people are like really, really like good at it, but you should try to avoid it because it is actually slower. People think coordinate bashing is super fast because they sort of like to avoid synthetic approaches sometimes. And it can be efficient and it can be good, and sometimes it is necessary. And I will not say that there are problems where coordinate bashing is not the fastest. There are, and I've had arguments with people about this. There are problems that are, you will need to, or at least need to some extent, bash them. But it may be tempting that it's a rectangle, but areas offer areas, like dealing with areas and dealing with lengths, all these things, you don't need coordinates all the time. And so similar triangles can be just as fast. In this case, you need the ratio of lengths anyway. So the ratio of lengths, and you can't really encode areas with coordinates as well, I think. Or at least you'll end up implicitly doing the same thing. Okay. Now a problem number 9. We are getting gradually harder. But this problem. Octagon ABCDE FGH, right? And so these sides are equal. These are all 10. And these are 6, 8, 10 triangles, right? So then this is, oh wait, sorry, I am being silly. These are not 10. These are 11. These are 10. And then these are 6, 8, 10 triangles. This whole thing is 23 by 27, right? And so we want to find the area of the polygon that is like the centroids of the vertices. Whoa, that's scary. That's really scary. What do I do about this? Like, oh no, there are centroids. I mean, what are centroids? Well, okay, let's first talk about that. Do you all know what a centroid is? Like, please let me know. This is like important, and I kind of want to talk about it because it's also like an areas thing. Yeah, you forgot. Understandable. Triangle centers are really confusing. Yeah, intersection of medians. Okay. So let's do that. Let's add the intersection of the medians. Then I know this is a bad drawing. Oh no, that was really bad. I can do that. I can. Okay, well, nice. Okay, so that and that. Okay, so this is let's just say any given triangle. Okay. So let's talk a little bit about the areas here, because this is actually an interesting result in and of itself. I am about to prove this fact that is important. AG over GM equals 2 over 1. Oops, okay. And maybe some of you have seen this before. I know that it is technically taught in like middle school geometry classes, but I don't know if all of you have exposure to those. So this thing. How do they prove this? Well, let's first talk about areas. We know that the area of ABM is the area of AMC, right? And I hope people understand, right? And then the area of BMG and GMC are also equal, right? So then here's the thing: the area of this and the area of this are equal, right? And so all three of these areas are equal, right? AGC and like CGB and BGA, they're all equal areas, right? And we see how we get this, right? Again, if you're lost, please let me know. And so then the area of this thing is, some constant C. And the area of this is like half of C, right? Because all the areas are the same. Then this is just 2 to 1, right? And that's how you prove it. Hopefully this is not too confusing. And if you have questions, use the Q&A, use the chat somehow, let me know, because I don't want to leave anyone behind. Okay, so this being 2 to 1 is important information. Why? Because we are actually, if you think about it, we're sort of zooming in. This is what is known as a homotopy. And so if I can, maybe I'll delete some of these. I'm sorry. This is okay. So each of these individual midpoints, right? These midpoints form a polygon, right? And it's this polygon, right? And what we're doing is we are taking a dilation of ratio 2 over 3. Do people see what I'm saying here when I say a dilation of ratio 2 over 3? We are like scaling the polygon out. We're zooming out. We are like projecting, right? So like this, right? We are sort of zooming in by a ratio of 2 to 3 when we take the centroids. That's what we just proved here, right? So then these things are all basically the new polygon formed by the centroids is similar, right? It has the same angle, same side ratio, same whatever property you want, and this is an important thing. When we zoom out, when we take a homotopy, when we take a dilation, then we are preserving everything. We are sending circumcenters to circumcenters, incenters, midpoints to midpoints, everything goes to itself under homotopy of dilation, right? Then the area of the area of the convex polygons whose vertices are the centroids, then this is just 4/9, right? Like for example, if I took a square, right, and I put a point here, and I zoomed in by a factor of 2, right, and I took this square, right, then this square would have area 1/4 of the original, right? And so this is sort of similar to what we're doing here. We are taking 4/9 of the area of the big polygon, and that's the area of the quote unquote smaller polygon. So are we all clear what we have to do now? Okay, That's good. So let's find the area of this thing. Okay, this big polygon here. How do we do that? Well, first of all, there's these two like trapezoids, right? This has height, 23, and this is height, midpoint of this length to this length, then that's, 17, 17, right? And so then, and this length is, 4 plus, 11 over 2, or like half of, this length, right? So then the height of this, what is the height of this? I know it's kind of confusing because I put a bunch of letters and numbers everywhere, but what is the height of this trapezoid here? And okay, I hope you're drawing a diagram at home because like, as much as I can try to provide like the experience, then like you might want to have a record. So what is the height of this trapezoid? Oh, 17. Okay, I got 17 by taking like this is a midline, right? So let me draw another thingy. Sorry, I know this is here. Then this length we know is 11, and this length we know this is 23, right? Then this length is like the what is in the middle, right? Which is 17, which is like 11 plus 23 over 2, right? Because this is the midpoints, right? And that's why I got 17. Okay, I do think that it is kind of. I think that you would be able, most of you would be able to execute this on an actual context. I will not be too annoying about the details. The height of the trapezoid is 19 over 2. The way you get this is sort of, and this is sort of like coordinate intuition. I'm going to erase again because I think that people know some of what's going on. I'm just going to erase everything because I think I have too many things that are floating around. Then okay, we're just going to isolate to this trapezoid for now and keep in mind the lengths of everything. Right? Then this little thing is 4, right? Sort of when we take the foot down here, this is 4. And this is 11 over 2, right? So this whole thing is 4 plus 11. The height of this thing is 4 plus 11 over 2, right? Which is 19 over 2. And again, we have 17 and we have 23. Okay, so now the area of this trapezoid is just, again, this is something that you probably saw in like middle school geometry classes or something. I'm going to erase some stuff. Sorry. Again, I know that people are taking notes, but it is also hard for me to teach. Right. So then the area of the trapezoid is this times this. Do people like know this? I think people do, right? Again, let me know if you're really like confused or don't know what the trapezoid area formula is, and I can go over it. But I think that most people here would know this. This is a fact that is, I think, widely known. Then this is, this is 20. And this is 19 over 2. And the area of each trapezoid is 190, right? So there's 2 of these are the same. And then there's a little triangle here. The base of this triangle is, length 17, and the height of the triangle is 4. And so the area of the triangle is 34. And so now in total we have, 380 from the 2 trapezoids plus 34 from the little triangle. Then we have an area of 414, and then all we need is 4/9 of this, right? Yeah, exactly. Thank you. We need 4/9 of this. And this is another thing. You need to remember to scale down. I am sure lots of people put 414, right? Because people always forget. So on your paper, you might want to write like 4/9 somewhere, okay? Because it's something important. Then we know that it's divisible by 9 because some of its digits is 9. And we can do a calculation. I'm going to try to do this in my head. I believe this is 46 times 4. And that should be, 164, which I believe is right. This is what I got in the actual contest, I believe, back in the day. That was 3 years ago. And so, yeah, this was actually the latest problem I solved on the 2018 AIME one. And so that's why I have a little bit of fun. But this is the idea, right? We have this really, really complicated statement, points in really weird places. And of course, again, you can coordinate batch this. No one is stopping you from coordinate batching this. This is very possible. But I will say that you probably should not, right? Because like you can find locations and like of course, if you knew what a centroid was, then you would know that it's actually, average or the center of mass of a triangle. Oh, someone raised their hand. Sorry. Yeah, Alexandra, what is, maybe you can post in the chat, maybe send me a private message. What is the problem? Or like, yeah, send me a private message. Because I saw a raised hand. Is there anything or? Okay. Yeah. Okay. So then you can obviously do a lot of work and you can get an answer and it will take time, right? But there is a reason this was placed at number 9, and this is not number 15 or something that is computationally intensive. Then you are going to want to do this in an easier way, which is why I did this sort of dilation thing. Because otherwise, finding each little point and then doing shoelace or whatever is actually going to hurt a lot, and it will take a lot of time. And I know people who do this. Like people just like decide, hey, I'm just going to go and get a hammer and bash away. And this is doable. But I think that here, I mean, just zoom in and do this sort of mock thing. By the way, this centroid 2 to 3 thing is used a lot. This is not the only time you will see this. I remember, I believe, almost in the same year. Well, no, the year after, I believe, 2019. Then there was a problem on the AMC 12, late problem, like number 25, I believe. That was an optimization problem, but it also used the same fact that centroids and the midpoints are on a 2-to-1 ratio. And that problem was interesting. I think it was a really, really interesting problem. I think that's one of the most interesting AMC geometry problems I've ever seen. But also, that problem made use of the same thing. And you can also use this. I mean, again, I said you shouldn't, but you can use it on this problem as well. I just don't advise it. And so this is something that does show up a lot. And you want to sort of know it, right? You want to be cognizant, because there are problems that are placed at positions that some people will get tripped up at. And I think this is a trend with a lot of recent AIMEs, and me and a few friends were talking about it. It was that a lot of recent AIMEs have really, really quote unquote hostile looking middle sections. And so what you're going to want to, so how you get an advantage over other competitors, I guess, is you are going to need to be able to parse things that look scary, because a lot of these problems, I think recently this year's AIME, for example, had some really, really intimidating looking statements, some really, really annoying problems, some really tricky ones. Then you're going to need to be able to understand what the problem is about, and you're going to need to be able to, and having this kind of knowledge can actually help you sort of figure out the problem faster, and having more knowledge, because some of the problems, of course, are not that hard. They just require some knowledge to make them a lot easier. I think this is true for a lot of recent AIME problems due to, certain proposers that I know. Then they are proposing problems that are deep and have a lot of knowledge and are not just bash and are not just like count this by multiplying and adding, right? There is increasingly a lot more quote unquote clever problems on the AIME. And so you are going to want to sort of learn at least some facts other than like, just bashing. I know there are people like, again, hold on a second. I'm going to skip this one. This one, this number 13 is notoriously hard, and I don't think I can draw a good diagram. This is the problem. I was going to do this, but then I totally like forgot how to do this like a few days ago, and I told myself I was going to solve this problem, and then now I realized that with the math prize example that we did earlier, then that is not going to happen, because there are too many points and they're all in a circled area 1 or whatever, and it's complicated. So I will not really do this one, but this one is another, one of those PIE of areas problems, and it also is an example of a late areas problem. People think areas is like some really, really silly thing that shows up early, and this is generally true, but you will see these in later positions. So that is one more thing. And I have about 5 minutes left, so maybe I'll just talk about a few of the problems in the problem set. I anticipated that I was going to be sending out a problem set, and maybe this is not the case. Is there a way for me to send you all a problem set in the chat? I don't think so. I'll ask later. Be prepared to receive a problem set. And there are, some problems, I think, in roughly order of difficulty. Some of these I think are very funny. And some of these I think are legitimately difficult, and they are in all sorts of positions, and they are in all sorts of contests that you may plan to go to, like HMMT, Math Prize, etc. All right, we'll do some of these easy ones because I think that these are like, I just didn't talk about these very much, and I didn't get to do any of these examples, so we're gonna do this one very quickly. Okay, so they each have area one, radius 1. Then they share a point of tangency, and so the area. Then you have like a rectangle of area 2 minus pi over 2, then like plus pi over 2. Then there's just like 2. Which is actually pretty funny. But anyways, yeah, this is an integer area. So there's a few of these sort of problems are in here. And then this is another similar problem, right? You take a hexagon and subtract a bunch of little circles. And so I started late, and now the next teacher is here early. Hello. Sorry. I know. This is another one of those, and then this AIME 4 here, number 4.3. I'm not going to go through all of them, but then there are also some area. This is an areas problem with much in this sort of style of subtract, add, put a bunch of triangles in a bunch of weird places. This problem in particular, actually, I am going to talk about 4.4. I think 4.4 is a good place to stop because this problem I think is like hard, and it is really the area solution is not intuitive. This one I did not even do areas on the official contest, but anyways. So there's a triangle and there's a little tiny square, and the corner of the square is 2 units away from the hypotenuse. And so I wanted to highlight the area solution to this problem because I think this is just incredibly mind-blowing. A friend of mine, you may know David Altizio, then he was talking about how this is ridiculous. I mean, this is so crazy. This problem is very, very cool because though you can bash it, and I did, and even I will say that, as someone who I always say, oh, I look down on this or whatever, then I still bash this. So, but there's an area solution. So let's talk about let's dissect the area into, a few pieces. Then, this, and I will not like, do the whole, I'll do the whole problem, but, so the area of the whole, so we dissect the area into 3 pieces, right? So there's a square, there's a triangle, and there's a distance, right? This is 2. Then let's dissect the area into 3 pieces. And let the side length of the little square be S. Then the area of this whole triangle is area 6, and this small triangle has area 5, right? So the sum of the areas of these little 2 triangles then is 1, right? But this is also 7 times S the side length over 2, right? That's the area of these 2 little triangles because they have bases 4 and 3 respectively. And so the side length of the square is 2 over 7. And then it's easy. It's just 4 over 49 over 6 is like 2 over 147, which is the answer. And so this is an example of how you can use areas and dissections to solve problems that aren't about areas. And I showed this earlier with the centroid example, but you can do problems like this. And so, yeah, again, I will be sending a problem set, but I think that is all I have for you today. I am sorry about, at least the students, for not being on time. But I hope that you learned something today. I hope that I was able to inspire you to not coordinate bash, and I hope I was able to teach you something useful.